About a year ago, I made a tutorial on how to create this pendulums animation on 3GS, and the math for it was pretty simple. Basically, I just used this single formula here to calculate each pendulum's position for each moment in time. And it feels like that the formula for a double pendulum shouldn't be much worse, right? Well, it turns out it is. It is much worse. And I feel like trying to fit this shit into a computer is gonna be a nightmare, so I decided to think about this problem in another way. So let's say we have a ball or any other physical object. This ball has a position in space, let's call it P. It also moves with some speed, let's call it V, and it's also affected by a force. It could be gravity, it could be something else, but for now let's just call it F. And what we want to do is, by knowing all these values for a frame or a tick or just a moment in time, we want to be able to calculate new position, speed, and maybe even force in the next frame or tick or moment in time, like this. And calculating these new values is not that hard. Let's actually just let's call them P1, V1, and F1. So P1 is just going to be P, the old position of the ball, plus velocity or speed times dt, where dt is the amount of time that passed since the last frame. And V1 is going to be V plus F times dt. F1 is going to be a little more complicated because it depends on other objects. For example, if it's the gravity, it's going to depend on how close our object to the ground is. So let's not think about it for now. But these things are pretty simple. It's just your basic school math, and it shouldn't be hard to code as well. I think usually this approach is called the Euler's method of solving bad equations, and it is just an approximation, so keep that in mind. Our simulation is not going to be perfectly accurate, but it's going to be good enough to look fine. Now let's try to actually implement it in code. So I will create a new project, a new Vite project, if I learn how to type. npm create Vite at latest. I will call it just pendulums. We can always change them later, and I don't have enough creativity right now. It's gonna be a vanilla project in TypeScript. Okay, cool. I guess it's time to open the VS Code. The first step would be to install the packages, obviously. And then we can just delete the stuff that was pre-made by Vite that we don't need. So in here, this counter file we don't really need. In the main document, we can safely remove this, and this. Then in the style CSS, we also don't really need anything, but let's keep the file because we will add some stuff into it later. And this typescript.svg file we also don't need. And an index.html, let's change the title to pendulums. All right, looking good. And now if we run our project, we will have this cool empty page. In order to render anything on the page, we need a canvas. So let's put one right here. And let's give it an ID of main canvas so we can easily access it in TypeScript. And that means in main.ts file, we can just create a variable and get the canvas by ID. And then we need to set its size to the window size. But as you can see right now, it doesn't really have a width or a height property. And that's because TypeScript doesn't really know that this is a canvas. It only knows that it is it's an HTML element. So we can cast it to the HTML canvas element and then set its width and height to the Windows width and height. But then if we look at the page after all that and try to see the canvas, we can see that it has weird paddings on the left side and on top, and also have these annoying scroll bars. In order to fix that, we need to add a couple of styles for the body element. First of all, we need to set the margin to 0. By default, it has non-zero margins. And also, let's set the overflow to hidden. Refresh. All right, much better now. We don't have scroll bars. The canvas is full screen. But keep in mind, if we change the size of the page, the canvas is not going to be full screen anymore because we only set the size on the page load. We can fix that later, but I don't think we should care about it for now. Now we're ready to start drawing. First, we need the 2D context of the canvas. Keep in mind that it can be null right now, so we can create like a guard for that. But we cannot just return from here because this is the top level code in the file. So let's create like a main function and put everything inside of it. And then using this context, let's just draw a simple circle. All right, looks good. Now we can actually make it move. The first step would be to create a new function called animation frame. It accepts time as a parameter, which is the amount of milliseconds that passed since the page was loaded. And now we can call window.quest animation frame. So this function is run whenever the browser is ready to render the next frame. But it's only gonna do it once. So if we want to run this function on every frame, we need to also do the same thing in the end of it. So this is kind of like recursion, but not really. But we don't really care about the time, the total time that passed. We kind of more care about the time that passed since the last frame. So I will create a new variable called last frame time and use it to calculate the delta time since the last frame. And I will also output it in the console. So now in here, when I refresh the page, we can see that each frame takes about 7 milliseconds, which kind of fits my refresh rate of the screen. Then we can create a couple of variables to hold the current circle position and speed. I will also fix a small problem with the context because right now, as you can see, it's nullable again because of hoisting or something, I'm not sure. And that can be easily fixed if I change this function into like a constant. Which is going to be the same thing, but I guess not really. And now it's not nullable anymore. Instead of having delta time in milliseconds, I kind of prefer it more in seconds. So we'll create a new variable called delta time seconds. Then I will use this delta time seconds to calculate the next position of a circle. And finally, on each frame, we can just clear the canvas and redraw the circle based on its current position. Okay, doesn't look like it's working. Oh, and here we need to actually add the distance covered to the Y position instead of just assigning it to it. And if we go here and refresh, don't forget to save the page. Okay, so now our ball is slowly falling down with a constant speed. In order to make the ball move in any direction we want, I will use X and Y for the speed as well instead of a single number. Let's set it to 40, 20. And then I will update the X and Y components of the position inside of the animation frame accordingly. Then, in order to make the ball look better, I will fill it instead of just stroking it, and I will move it slightly lower. All right, looks a lot better now, and it moves kind of sideways. So now these two things actually have the same structure. They are essentially 2D vectors. So let's create a new type for that. And then in the animation frame, we can create a couple of functions to help updating the circle position based off the speed and delta time in seconds. The first function is going to be an add function that will add two vectors together. And the second function is going to be a scale function that will multiply a vector by a scalar. And now in here, instead of updating this one by one, we can just do circle position equals circle position plus circle speed times delta time in seconds. And that means we cannot have it as constant anymore, so let's just let it. Okay, and it works the same as before, so our refactoring didn't break anything. Now to make it more interesting, let's update the speed as well. And that means we need some kind of a force, so let's define a gravity as another vector. And then on each frame we will also update the speed the same way we update the position. I will also update the initial values a little bit, just so the initial speed points top right. Alright, looks pretty good. It kind of resembles real-time physics already. But what if we wanted multiple circles? Let's create a couple types first. So we will have a type for a body that will have a position and a speed. And then we'll have a type for a world or a scene. It's like something that defines our, well, physical world. Right now it's just gonna be a list of bodies. Okay, and then inside of our main function, we will define a couple of bodies. And then our world is just gonna be these two bodies inside of it. Then on every frame, instead of just updating the circle speed and circle position, we can actually delete these right now. Instead of doing this, let's update every body of the world. The mass is gonna stay the same. And then instead of just drawing a single circle over here, I can actually do this. Instead of drawing a single circle over here, we will just iterate over every body in the world, and we will draw the circle for each of them. Alright, should be good now. Let's try it out. Okay, we now have two different worlds with two different speeds, but the code is essentially the same. And if we want to try another one, we will just have to create another body and put it in this list, and that would be it. You know what? Let's also move this gravity constant inside of the world structure as well. Usually I like to make things work before trying to organize the code or refactor it or split it into different files. But right now it feels like there is already a lot going on in the main.ts file, and especially in the main function. So let's try to clean it up a little bit. The first thing we will do is extract the world initialization from the main function. And then we will do the same for updating the world and drawing it on screen. Our update world function is gonna be a pure function, so it will receive a world as a parameter, and it will return a new world as a result. That means our world cannot be a constant anymore. Oh, and the update world function will accept delta time in seconds. Now let's try to split this file into multiple ones. And let's start with this part, because this is just defining a vector type and a couple of operations on it. And we can easily move these into a separate module. So I will create a new file called vector.ts. In here, I will define a new namespace called vector, so it's easier to use. And I will just cut this thing and paste it into it. Don't forget to export pretty much everything. And then in the main.ts file, I will import the vector namespace. And that means I need to prepend everything vector related with vector dot. Now I can do pretty much the same with the physics system. I'll create a new file called physics.ts. And in this file, I will create a namespace called physics. And this namespace will contain these four things: the body type, the world type, the init world function, and the update world function. And after that, I can just fix the types in the main.ts file and import the new physics package. And finally, I will do the same with the render functionality. We'll create a new file, call it render.ts, and then this will have a new namespace called render. And for now, it will just contain a single function called drawWorld. Actually, now that I think about it, it feels like the init world function from the physics package should actually be moved back into the main.ts. And the reason is I want this physics file, this physics namespace, this module, to only have the tools that the other code will use. So no predefined values, nothing like that. And this thing here is the function that like initializes the scene, and it has the concrete values for our first bodies, for the gravity force, and other things that we will add here later. So I think it belongs here, at least for now. All right, in my opinion, now the code looks a lot better and cleaner. Let's check if we broke anything. Doesn't look like it. But this thing here, it's not really pendulum, right? Or double pendulum, or anything we wanted to create in the first place. And we lack one more thing to actually create a pendulum, and that is constraints. So let's think about the pendulum for a second. Basically, we have two physical bodies, one over here and one over here. And right now we will just talk about a single pendulum. And this guy over here has like a speed or something. It's affected by force, by the gravity. This one over here is also affected by the gravity. But if we don't do anything about this, what will happen is this body will move down. This one will move like here. Its speed is going to be updated. And this is nothing like a pendulum. What we want is we want this body to always stay in one place. And we also want the distance between these two bodies to always be constant. So that means we need two different types of constraints. The first one is going to be a static constraint, or at least that's what I will call it. And the other one is going to be the distance constraint. And let's think for a second about how we can make them work. There's multiple ways to go about it. For example, I can pretend that this thing is some kind of a spring. So if these two bodies go further from each other, there is like a force that tries to bring them closer. Or we can do something like more mathematically advanced and try to do all the calculations at a different coordinate system or something. But I wanted the easiest solution ever. So what I will do, for example, for the static constraint, I will apply the force and the speed to the body that will move it down. And then I will check if its coordinate is different from the coordinate of a constraint. And if it is different, I will just move it back. And the same thing for the distance. After I do the calculations for the bodies, let's say this one moved over here and this one moved over here, I will check the distance between them. and if it is further than what I want it to be, I will just move both of the bodies closer together and call it a day. So let's try to code it and see if it works. So let's start with a static constraint first. In the physics file, I will create a new type called static constraint. And this thing will hold a position, which is a vector. And it should also hold some kind of a reference to a body that we want to constrain. One way would be to just hold an actual reference to a body, but usually I like to work with IDs more than references like this. So this will a body ID with the type of a string, and that means we need to add an actual ID to body type. But now the problem is when we create a body, we need to assign it a unique ID. And instead of doing it here, I kind of want the ID generation to be a part of a physics library. So I will create a new function called createBody, and then I will just generate that ID inside of a function. That will be some kind of a constructor for a body. Instead of just listing all the properties we want here, like position and speed, I can just tell TypeScript that I want the whole body type except for this ID field using a thing called emit. And now I can see that this props thing here, it only has a position and a speed, and that's exactly what we need. So we'll create a new body in here with the randomly generated ID. And for generating the ID, we will use the built-in crypto library that should be supported by pretty much all the browsers right now. All right, and then we will use this function in the main.ts instead of filling the fields ourselves. So this will be, we will still need pretty much the same thing we specified here before, but I think right now we don't need to set the type anymore because this will be derived automatically, yes. And let's do the same thing over here. All right, now that type bodies have IDs, let's actually also add an ID to a constraint as well. We won't need it right now, but we will probably use it later. And that means we need the constructor for the constraint, similar to the createBody function. And after we did all that, we can actually create a constraint in the main.ts file. Let's try to do it. And this constraint will just hold the first body in the same place. After that, we need to somehow put the constraint into the world. That means our world type needs another field called constraints. And then here in the main.ts, we can put this single constraint we just created inside. It's not gonna work yet because we don't apply it anywhere. To do that in the physics.ts, in the update world function, after we calculate the next positions and speeds for our bodies, let's also apply the constraints one by one. In the case of a static constraint, it's going to be pretty easy. First, we need to find the actual body that we need to apply the constraint to. And then we just need to adjust its position to the position of the constraint. And then replace it in the next bodies array. It's not very optimized right now, and maybe at some point we'll use like a map over here or something like that, so the lookup for the ID is faster, but right now we don't really care about that. And the good news is, if we switch back to the browser and refresh the page, we can see that the first body is indeed static right now. So it turns out our code kind of works. Now we can add a constraint for the distance. So let's create a new type called distance constraint. And it will just have two IDs of two different bodies and the distance as a number. And then I kind of want to be able to differentiate between these two things. So let's add a type property that will just be static for a static constraint and the distance for the distance constraint. And then I kind of want to have a constructor for the distance constraint as well. And let's create a type that will be just called constraint, and it will be a union of these two types. That means now we can define the constraint list of the world as just a list of constraints. And then when we will apply them, we will check for the type. So right now this doesn't work. But if we add a check for the type, and if it is static, we will do the same thing we did before. And then if it is distance, we will do the distance constraint in here. All right, looks good. And then in the main.ts, this thing doesn't work anymore because it expects us to pass a type. And I don't really want to do this because we already know that we are creating a static constraint. So the only option would be, let's see, type static. So let's just do that in the constructor as well. That means in here, we also need to omit the type property and just set it inside of a constructor. And let's do the same thing for the distance constraint. This is going to be distance. Okay. Yeah, it's a little bit angry about this, but it's fine. And the types in the main are fine now. So let's try to actually implement a distance constraint. So in here, first, we need the actual bodies. We can get them by the IDs. And now let's calculate a few different things. The first thing, we need the offset, which is going to be a difference between the actual distance between these two bodies and the desired distance of a constraint. And for this, I need to add a couple more things to the vector library. So let's do it right away. The first thing we want in here is the length, which is going to be the length of a vector. And that's pretty easy. It's just the square root of the squares of both of the components, basically. By the way, I'm not going to explain all this math. I'm kind of counting on you knowing the basics of the vector math. But if you have any problems, just leave a comment. All right, and using this length function, we can do a distance function, which is going to be a length of the... Actually, first we need a subtract function. Yeah. Subtract is just going to be like an add function, but with the minus signs here and here. All right, and now if we subtract one vector from another, and then we get the length of the result of that, we will actually get the distance between 2 points if we consider vector as points. All right, looking good. I hope I didn't make any mistake here. And now we can go back into the physics file, and this distance offset, it will just be a distance between the first body and the second body minus the distance property of the constraint. Then we can calculate the direction for each body in which it needs to move. So, for example, if the distance between two bodies is greater than the distance of the constraint, these two bodies need to move towards each other. Actually, we want the direction to be normalized vectors, want directions to be normalized vectors. So let's go back into vector.ts and add one more thing in here. So the normalize function will just set the length of a vector to 1, keeping its direction intact. And we can do this by just scaling the vector, dividing the vector by its length. So it's scaling it by 1 over its length. All right, very good. So yeah, let's create the direction. So the first body, let's call it first body just direction. It's just gonna be a normalized vector between the first body and the second body. And to get the vector between we can just subtract them. So it's gonna be vector normalize of vector subtract first position and second position. Actually, it's the other way around. It's second position minus first position. And then the second body direction is going to be the same thing with just these two things in reverse. Actually, I lied a little bit. These vectors are going to always be in the direction of the other body. So this vector will be always towards the second body, and this vector will always be towards the first body. And then the distance offset sometimes will be negative, and that will affect that will be how we handle two different cases. Like if the distance between two bodies is less than the distance between a constraint, is going to be negative, otherwise it's going to be positive, and that will affect how the bodies will actually move after we apply the constraint. So now let's calculate the adjustments for each bodies. Basically, we won't be thinking about masses right now. Let's pretend that all our bodies have the same mass. So in order to apply the constraint, we just want to move both of the bodies in the directions of their adjustments by the distance offset divided by 2, right? So let's calculate that right now. All right, now we have the adjustments for the bodies, and all that's left is to apply them. So for the first body, I will create a new vector that's going to be this new position. Then, yeah, let's create a new position first. I will call it first body position constraint. And I will just add the adjustment to the position of the first body. Then I will calculate the first body as a whole, but also constraint. That will just be the first body, the clone of the first body, but with the position changed to the first body position constraint. All right, and finally, I will replace the initial first body in the next bodies array with this constraint first body. Okay, and then I just need to do the same thing for the second body. And finally, let's go back to the main file. And in here, I will create another constraint, which is going to be a distance constraint between our two bodies. I will also add it into the constraints array of the world. And then I will move our bodies a little bit closer to the center of the screen. And I will set their speed to 0. Okay, let's switch back to the browser. It doesn't look like it's working. All right, first of all, this should be width divided by 2 plus, let's say, 400. Okay, but it's just falling down. And that's because I made a slight typo in the vector.ts. So in here, I just subtract vector2.y from vector2.y. And this should be vector1 actually. And now if I switch back, we can see that the constraint kind of works, but for some reason the second body just stops down here. It doesn't really swing back and forth. So let's try to see what's wrong there. So we could try to console log something, but I feel like reading a console output that outputs like 140 times per second would be a nightmare. So we would have to limit the frame rate or do another trick. So I want to like approach it from a different perspective and try to make it a bit more visual. So let's try this. We'll go into the render.ts file. And in here, for each body, we will also try to draw its speed as a line. And I will also try to like do the context save and context restore for each shape I'm drawing, so I can avoid stupid mistakes. All right, let's see what it looks right now. So as you can see, even though this body stops right here and this doesn't move at all, the speed keeps growing and growing and growing, and it always points downwards. So what is going on here? Let's try to do a drawing again. So here's our first body, which is a static one. Here's our second body, which is linked to the first one, and the distance between them should always be the same. And if you think about it, it kind of means that the second body should always be on this circle around the first one, because the radius is going to be the same. And let's say it just started moving, so it has an initial speed. It just got affected by the gravity, and the gravity increases speed downwards. And then we will update its position by moving it downwards. And then we also need to make it satisfy the constraint, which would be moving it closer to the first body. But if we think about it, the speed is never gonna change its direction, because on the second frame, it's gonna grow a little bit because it's gonna be affected by the force more. We will move it down, then we will move it back to satisfy the constraint, and we will just do the same thing over and over and over again until it reaches this point down here, and then the speed is just gonna keep growing, but on every frame, we will just return it back to this circle. And the second body over here, will never have an incentive to move left. So here's how we're gonna solve it. This is gonna be pretty much the same procedure as we had before, with one little detail. So let's say we do pretty much the same. We apply the force, we apply the speed to the position, we move it to satisfy the constraint, but then we will also update the speed. And the way we will update it, we will just see how much it moved since the last frame. And we will say that the speed is just that. So it moved from here to here. So the speed is just going to be pointing here with like this value or something. And let's see if it works or not. Let's go back to the code. In order to make this work, let's go back to physics.ts file, and we need to update this piece of code here. That's where we apply the distance constraint. So first of all, right now we're only working with the bodies after their positions and speeds were updated due to the force, or like the positions were updated due to speed. But we also need to check the position of the body before anything changed, like before this update world was even called. And that means we need to remove these into like next first body and next second body. And then we need to find the initial states of our bodies. All right, after that, somewhere in here, when we are trying to find the position constraint of the first body and of the second body, let's also calculate the first body speed constraint, which is going to be pretty much the same I told you before. It's going to be like the new position minus the old position, and then divided by the frame length, because the speed is like how much is going to move per second, and this is how much it moved per frame. And then we'll do the same thing for the second body. And we should also not forget to put the new speeds into the new bodies that we create over here. All right, I think that should be pretty much it. Let's go back to the project, and we can see that right now nothing moves at all. So what the fuck happened? And also it looks like the speeds are not even growing at all, right? Because there is no green line or anything. Let's look at the code and try to find out what's wrong. And the reason is for that is pretty simple. Let's try to track what happens with the bodies. So first of all, in the main.ts, we initialize both bodies with 0 speed, right? Then somewhere in here, we update the position using the speed. That means the position is going to stay the same. Then we update the speed by the force. So the speed is going to be like not 0, right? But then remember, our position stayed the same. In here, when we apply the constraint, we don't even move anything because the position stayed the same, as I said, and it already satisfies the constraint. But then we try to update the speed again. And it turns out if we do this, subtract the constrained new position from the old position, which are the same positions, we're gonna get 0. So basically, in here, we're gonna set the speed to 0 again. And then we're gonna go into the next update world function and gonna do the same thing again, and then set the speed to 0 again and never move anything. And in order to fix that, we need to just do one simple thing over here. Because what if instead of applying the position first and then changing the speed, applying the speed to the position first and then changing the speed, we will calculate the speed first. And then in here, you find the next position. We will use the next speed instead of the current speed right here. All right, moment of truth. And it works. Finally. It kind of resembles a pendulum, right? And that means now it's time to add another body and see if our double pendulum actually works or not. Here in the main function in the main file in the init world function, we will create another body, the third body. Then I will also make a third constraint over here. Before showing you the result, I kind of want to update a couple more things. So first of all, in the main.ts function, instead of updating the world once per frame, we can actually use something called substeps. So basically for every frame, we update the world like 10 times, for example, and that's gonna make our simulation a bit more accurate. So let's just do that. We can afford to do like 10 because our calculations are very, very, very lightweight right now. We have like 2 objects, like 3 objects and a couple constraints. So we can afford to do it like 10 times per frame. Let's just do that real quick. Just remember that the new delta time that we pass into the update world function is gonna be 10 times less. So we need to divide this by substeps. And the next thing I want to change is I want to update the graphics for the simulation. And that means in here, first of all, I want to fill the whole scene with like a dark color. Then I will also change the colors for the bodies and for the speeds. I will actually keep the speeds visible because I think it kind of cool how they look. I will just make them twice as short. And then finally, I will also draw the constraints as well, just like little like lines or ropes between the bodies. And it only applies to decent constraints, of course. All right, I think we're good. What's the... Oh, I think I forgot something like this. Okay, I think we're good to go. Let's see how it looks right now. All right, pretty cool. And looks pretty accurate. If I imagine a double pendulum, that's kind of how it would move. A little bit chaotic, but this is it. So there is a lot of things that we can add to this project or improve, or maybe like new physics rules, new objects, new constraints, or maybe try to make it very optimal or something like that. But this video is getting way longer than I expected already. So if you guys are interested in stuff like this, just let me know and we can turn it into a series or something. We'll see. Thank you for watching, guys, and I'll see you next time.